the administration had changed my testimony. But anyway, so there have been various congressional hearings, including Al Gore's and other senators and representatives. In putting together my slides last night, I had two different titles, I realized, and I wasn't sure. One of them was about avoiding dangerous climate change, and the other one was about how sensitive is the Earth's climate. And those are obviously very closely related subjects, and I will be addressing both of them to some degree. And there is a lot of material here, so I will have to go over some of it pretty quickly. So I want to just make clear what the bottom line is, as far as I'm concerned. And I hope that comes through in the discussion. But it seems to me that there is a very big gap between what is understood about global warming by the relevant scientific community and what is known about global warming by the people who need to know, and that's the public and the policymakers. And we need to try to close that gap because we're running out of time in trying to do something about about what is, in fact, a climate crisis. It turns out that the Earth's climate is dominated by positive feedbacks on both intermediate timescales and long timescales. It didn't have to be that way, but it turns out that both the water cycle and the carbon cycle lead to some strong positive feedbacks. And the result is that the response of the climate system to the gases that humans are putting into the atmosphere, primarily by burning fossil fuels, but the climate's response to those changes is still in the process of occurring. And there is additional global warming that's in the pipeline, which is going to occur without any additional changes in greenhouse gases. And the climate system has now reached a point such that some of the positive feedbacks are beginning to happen, like a good example is the Arctic sea ice. The amount of Arctic sea ice has been decreasing several percent per decade the last 25 years. That's a strong positive feedback because as you lose the sea ice, then the Arctic Ocean absorbs more sunlight, and that causes more warming. And another very important slower process is the response of ice sheets to the change in global temperature. We now know that both Greenland and West Antarctica are losing ice. At least over the last 5 years, they've been losing ice. And over the last, almost 5 years that the satellites have been making measurements of the mass of these ice sheets, they're losing mass at a rate of about 150 cubic kilometers per year. So we're at what I call a tipping point, where if we don't need much more forcing in order to cause some very large changes, which basically will produce a different planet. But the warming that we've seen to date, this is global average surface air temperature from 1880 to the present, and there's been an increase of about 0.8 of a degree Celsius, with 3/4 of that warming occurring in the last 30 years. And, well, that doesn't seem like a lot of warming in comparison to weather variations of temperature, which can be 5 or 10 degrees Celsius. it's not very large, but in fact it's very important and is going to have important effects. But you know, the temperature at a given place depends much more on what direction the wind is blowing from than it does upon how much greenhouse gases you've got in the atmosphere. I mean, the variations from day to day depend on what direction the wind is blowing from. Whether if it's blowing from the north, it's different than if it's blowing from the south. And even if you average the temperature over a month, the temperature anomaly relative to some period of climatology is very dependent on the weather variations that occurred during that month. So here are the temperature anomalies during the last 4 months. And these are anomalies relative to the period from 1951 to 1980, which we define as the period of climatology. And that's when many middle-aged people grew up. But you can see that the anomalies are in degrees Celsius. So the yellows and reds are warmer than the long-term average, and the blues are colder than the long-term average. So if you look at a given place, like the eastern United States, it was very warm in January and then cool in February and warm again in March, and then April was quite cool. So people thought it was a very long winter because April was cool. And I guess if we looked at Tel Aviv, January looks like it was fairly normal, and February was perhaps warm, and March, again, maybe a little warmer than normal, and April quite cool. But if you look, most of the planet is warmer than normal, and the average, in fact, January is the warmest January in the 130 years of record. February was the 5th warmest, March the 4th warmest, and April the 2nd warmest April. So if you average the anomalies over the first 6 years of this century, then you sort of lose those weather patterns. And you see that it's consistently warmer than it was in 1951 to 1980. And the patterns of warming make sense. The warming is larger over land than it is over the ocean because the ocean has a lot of thermal inertia. So if you apply some forcing by increasing the amount of greenhouse gases, so it tends to warm the planet, well, the ocean is going to warm more slowly because the ocean is 4 kilometers deep and it takes it a long time to respond. So there's more warming over the land than over the ocean. There's more warming at high latitudes than low latitudes because of the positive feedbacks that occur at high latitudes, primarily the decrease of the snow and ice area. And there's more warming in the northern hemisphere than in the southern hemisphere because there's more ocean in the southern hemisphere and because the southern ocean mixes quite deeply. And so that increases the response time. Okay, to understand climate sensitivity and what we can expect in the future, it's very useful to look at the history of the Earth. This is the temperature in Antarctica for the last 400,000 years, with time running from left to right. And this temperature is deduced by drilling a core in the Antarctic ice sheet, which the Antarctic ice sheet is a few kilometers thick, and it's built up from snowfall that piles up year after year and is slowly compressed into ice. And by drilling a core to the base of that ice sheet, we can sample the snowfall that fell as a function of time over this 400,000 years. And from the isotopic composition, the amount of oxygen 18 and the amount of in the frozen H2O and the amount of deuterium as opposed to hydrogen for the H, it depends upon the temperature at which the snowflakes form. And so we can get a measure of the temperature as a function of time. And you can see that the climate has fluctuated by about 10 degrees Celsius between the cold periods and the warm periods. The warm periods are less frequent and briefer than the cold periods. Yes, this is supposed to be my pointer. It's hard. It's a little hard to do this. But anyway, this is the Holocene. The warm period that we now live in is now almost 12,000 years. Am I supposed to do something with this? Oh, okay. Thanks. It's now almost 12,000 years long. And it's several degrees Celsius warmer than it was during the last ice age, which peaked about 20,000 years ago. Now, one thing that we can do with this data is investigate this question of climate sensitivity to a forcing. Now, a forcing is an imposed perturbation to the planet's energy balance. For example, if the sun became 1% brighter, that would be a forcing of 2.4 watts per meter squared because the Earth absorbs 240 watts per meter squared of sunlight. Now, so let's, and we know the conditions during this last ice age, 20,000 years ago, quite accurately, and can compare that with the conditions during this current warm interval. We know the conditions both in the atmosphere and on the surface of the planet. And we know, by the way, that the sun has not changed very much in its brightness over that period. It may have changed. The sun's brightness changes by about 0.1% as you go from solar maximum to solar minimum with 11-year cycles. And the sun is slowly getting brighter over time by about, I believe, about 10% per billion years. But so on this time scale, it would be a negligible change. But the atmospheric composition has changed. You can see that the amount of carbon dioxide and the amount of methane is very highly correlated with the temperature. And for expected reasons, when the planet is warmer, there's more carbon dioxide in the atmosphere because when the ocean is warmer, the solubility of carbon dioxide in the ocean decreases as the temperature increases, so that more CO2 is going to come out of the ocean into the atmosphere when the ocean is warmer. And we know that during the last ice age, there was an ice sheet that covered Canada and reached down into the United States, and there was another ice sheet in Europe, in northern Europe, and because of these changes on the surface of the planet, there was greater reflection of sunlight and therefore less solar heating of the planet. And those changes are known quite accurately. This ice sheet and the changes in the vegetation that existed caused a forcing of about 3.5 watts per meter squared. And the change in the amount of greenhouse gases caused a forcing of about 2.5 watts per meter squared. So that, and these changes maintained a planetary temperature difference of about 5 degrees. The temperature variations from the ice age to the interglacial are about 10 degrees at the pole, but they're only about 3 or 3.5 degrees at the equator. And averaged over the planet, the temperature change between the glacial and interglacial is about 5 degrees Celsius. So this implies a climate sensitivity of about 3/4 of a degree for each watt of forcing. That happens to be the same climate sensitivity that you get with global climate models. And in 1979, the National Academy of Sciences in the United States had a study chaired by Jewel Charney in which they looked at this question of climate sensitivity and looked at global climate models and estimated that for doubled carbon dioxide, you would expect an equilibrium warming of about 3 degrees for doubled carbon dioxide. And doubling carbon dioxide is a forcing of about 4 watts per meter squared. When you increase the amount of greenhouse gas in the atmosphere, that makes the atmosphere more opaque in the infrared region, and therefore the radiation to space from the atmosphere is going to emerge from a higher level in the more opaque atmosphere. And of course the temperature is falling off with height. Therefore it reduces the emission to space, or stated differently, these greenhouse gases trap infrared heat radiation. And so both the models and this empirical evaluation tell us that sensitivity is approximately 3 degrees for doubled CO2, or 3/4 of a degree for each watt of forcing. And now we can check this sensitivity over a much longer time period, because we have, from measurements of sea level in the Red Sea, we know the change of sea level over this entire 400,000 year period with a reasonable accuracy of about 12 meters. You can see that as the temperature of the planet was changing, the area of ice sheets changed and the sea level changed. The water which is not in the ocean is the water that's locked up in these large ice sheets, that, especially the one that covered Canada. And we know that the area of the ice sheets is going to approximately go like the 2/3 power of the volume of water, because the ice sheets are going to get bigger in both horizontal dimensions but also thicker. So the horizontal area of the ice sheets will go roughly like the 2/3 power. And so we can calculate, based on the fact that the forcing at the last ice age was 3.5 watts due to the albedo change, we can calculate the forcing at all points in time due to the change in ice sheet area. But also we know the greenhouse gases as a function of time, because in these ice cores in Antarctica, as the snow is compressed into ice, it traps bubbles of air. And so we have samples of the Earth's atmosphere as a function of time over this entire 400,000 year period. So we know the forcing by greenhouse gases and ice sheets, and if we just add those two up and multiply by 3/4 of a degree per watt, we get a predicted temperature change shown by the blue curve, and we can compare that with the observed temperature, which is the red curve, and you can see there's a remarkably good agreement, which tells us that the climate sensitivity is the same as a function of time, and it's roughly 3/4 of a degree for each watt. And this, however, another important point is the timing of the temperature change and the greenhouse gas change. And so here I've plotted the greenhouse gas forcing. So this is actually the forcing due to greenhouse gases is due primarily to carbon dioxide, but also methane, significant part of it, and nitrous oxide. But if we compare that with the temperature change, there's obviously a very high correlation. But if you look at the timing very carefully, you see that the temperature leads the greenhouse gases slightly. Well, slightly is several hundred years. So the temperature is changing first, but that causes the ocean to release carbon dioxide, and it causes the increase in the greenhouse gases. But in turn, primary mechanism by which the temperature increases, there are two mechanisms, and I showed you those. The two mechanisms are the changes in atmospheric composition and the changes in the surface albedo, or the reflectivity of the surface. So something else is instigating these changes, but in fact then the mechanism for the temperature change is these two mechanisms. And of course the mechanism that the instigator of the changes is changes in the orbital elements of the Earth. The most important one being the inclination of the Earth's spin axis to the plane of the Earth's orbit. At this time, the spin axis is tilted about 23.5 degrees to the Earth's orbit, but that wobbles because of the large planets, Jupiter and Saturn, are tugging on the Earth, and also Venus comes close to the Earth and is pulling on it. And we can calculate very precisely the effect of these gravitational tuggings of the different planets. And that tilt of the Earth's axis, it just continually is changing with a 41,000-year periodicity. Also the ellipticity of the Earth's orbit. It's sometimes almost a perfect circle, but other times it's slightly elongated, elliptical, again because of the tugging of the different planets. But the most important one is this inclination of the spin axis. And if you look at the temperature of the Earth, this is now over the last 3.5 million years. And this is delta 18O is we don't have ice sheets going back more than about 700,000 years, but we have ocean cores. And in the surface waters of the ocean, there are these microscopic animals, foraminifera, which are shelled animals, and as they die and sink to the bottom of the ocean, they pile up in the sediments of the ocean, and you can, just like on the ice sheets, you can take a core of the ocean sediments and get a record as a function of time of the composition of the shells. And the oxygen isotope depends upon both the sea level and the temperature of the ocean. So as we go from 3.5 million years ago to the present, the planet is slowly getting colder, but it's also fluctuating temperature. And if you look carefully, you'll see that those fluctuations are occurring with a 41,000-year periodicity. Up until 1 million years ago, when the periodicity became more complicated, because that was the time at which this large ice sheet over Canada began to be so large that it would not completely melt on a 41,000-year periodicity. But one other important point is why has the Earth been slowly getting colder? Well, almost certainly that's due to the fact that the amount of carbon dioxide in the atmosphere has been slowly declining over this time period. Because the last few tens of millions of years have been a period of rapid mountain building. Both the Andes, because the South American plate, as it's sliding westward, is hitting a rough spot, and the Andes have been growing quite rapidly. It's hard to measure the change in the mountain heights, but there are ways to do that from the estimated surface pressure. And between 11 million years ago and 7 million years ago, the Andes was growing at approximately 1 millimeter per year, which is a very fast rate because that's 1 kilometer per million years. So over that 4 million years, the Andes went up 4 kilometers. And when mountains grow more rapidly, then they weather more rapidly. You get heavy rainfall on them, and that forms then carbonates, which are then deposited in this ocean surface, ocean bottom, and that draws down the amount of CO2 in the atmosphere. And also, I should say, the Himalayas have actually been growing rapidly during the last few tens of million years. So, now there's one other important piece of data, and that's the fact that these greenhouse gases, this is methane, you can see is now increasing off the chart, and carbon dioxide likewise is increasing very rapidly. And I've added on the last century with the time scale greatly expanded, just so you can see the change. But you can see that now, and of course these increases in methane and carbon dioxide are human-made, due primarily to burning fossil fuels. And we're driving the amount of these gases completely outside the range that has existed for hundreds of thousands and even millions of years. And the temperature is beginning to respond. The temperature is beginning to warm up. It takes time to respond. But there are several conclusions we can get from these paleoclimate data. As I mentioned, these mechanisms, the two mechanisms that cause the temperature change, the change in the surface albedo and the change in atmospheric gases, are feedbacks. The instigator is a very weak forcing. I mean, just these small changes in the Earth's orbit are really very weak forcing, but they cause very large changes because of these positive feedbacks. But now, the human-made forcings are much larger than the natural ones. Humans are now completely in control of global climate. And one thing that, in order to understand and predict the effect of these human-made changes, we need to know something about the response time of the climate system to a forcing. That depends upon climate sensitivity to some degree, but we can calculate the response function with a global climate model. It has to be a model that includes the ocean as well as the atmosphere, because it's the ocean that gives the physical climate system its inertia. And what we find when we run a global climate model is that you get about half of the response after about 30 years. It's related to the amount of mixing in the ocean, so that the mixed layer can respond quite quickly. I mean, you get significant response in the first several years, but then as you get mixing of ocean between the mixed layer and the deeper ocean, it takes a long time. After a century, you still only have 60 or 70% of the response, and it takes, even after 1,000 years, you've still got only about 90% of the equilibrium response. But anyway, we have these global climate models, and we can use them to estimate what is the effect of all of the forcings that are being applied to the system. And the largest forcing seems to be the increasing greenhouse gases, which now is causing a forcing of about 3 watts per meter squared. There are other forcings that we know quite accurately. One of them is due to volcanoes. This is Krakatoa. When a volcano puts sulfuric acid into the stratosphere, sulfur dioxide that becomes sulfuric acid, the particles in the stratosphere reflect sunlight, and that causes a cooling effect, or negative forcing. And and there are small variations of the sun, about 0.1%, so that goes up and down. And the one important forcing that we don't have very accurate measurements, but it's a negative forcing, and that's the human-made small particles in the atmosphere, especially sulfates, again due to burning fossil fuels. But that reflects sunlight and causes a cooling. Well, if we just accept these estimates of the forcings and put those in a climate model which has a sensitivity of 3 degrees for doubled carbon dioxide, then we get a warming, or we get a temperature changes over the last century, which are in quite good agreement with the observations of temperature during that period. And you could say, well, if the model had, and this is with the model with sensitivity 3/4 of a degree for each watt, you could say, well, if the forcing was larger and the model sensitivity was smaller, then we could have got equally good agreement, and that's right, or vice versa. But the sensitivity of the model is the same as we infer from paleoclimate analysis. And we can then extend the calculations into the future, and if we continue with what is called business as usual increases in fossil fuel use, the calculated warming by the end of the century is about 2 to 3 degrees Celsius. I contrast this with the scenario in which we call the alternative scenario, in which it's assumed that the fossil fuel use will flatten out now and by the middle of the century be 20 or 30% less than it is now, and then by the end of the century it will be reduced enough so that the atmospheric composition stabilizes. That would require a reduction of probably 60 or 70% in fossil fuel emissions. And with that scenario, the warming is kept less than 1 degree Celsius. And the reason that we thought that was important is that if we look, it's been agreed by essentially all the nations in the world, 160 or 170 nations signed this Framework Convention on Climate Change in 1992, in which it was agreed that we had better stabilize greenhouse gas emissions at a level that avoids dangerous human-made interference with climate. Now, the problem is that no one has defined what that means. What is dangerous interference? And I had suggested, based on the history of the Earth, if you remember the first graph that I showed, the glacial to interglacial, there were some previous interglacial periods that were warmer than the Holocene. And they were up to almost 1 degree Celsius warmer than the current interglacial period. And it was still basically the same planet. There was still sea ice in the Arctic, and sea level it may have been, in some of these interglacial periods, it may have been as much as 4 or 5 meters higher, a few meters higher than now, but it wasn't a different planet. I would say that the climate during the Pliocene, the middle Pliocene, about 3 million years ago, I would say that's a different planet. Then it was about 2 to 3 degrees Celsius warmer. There was no sea ice in the Arctic during the summer, and sea level was about 25 meters higher, which is about 80 feet higher. That would be a catastrophe. So I think we cannot go down that path of business as usual, because we will eventually end up with a different planet. How long it takes the ice sheets to respond is a point of debate at the moment. But I think that appropriate metrics for dangerous climate change should start with those things that are irreversible. If the ice sheets disintegrate, it would take tens of thousands of years to rebuild those in a natural way. And so that's an irreversible change. Likewise, if you exterminate species that's an irreversible change. And I think a good criterion for defining what is dangerous impacts. And there are also very large regional climate changes that may be important. And as I mentioned, if we look at the history of the Earth, this is for the last 1,350,000 years up to the present, there were some periods. So this is the, and again, I've expanded the time scale here on the right. So in the last 130, 135 years, this is the temperature, and it's been getting warmer during this period. This happens to be the temperature in the western Pacific, the so-called warm pool. This is the warmest place on the planet as far as the ocean is concerned. And it's probably the single most important point on the planet because the transport of energy from low latitudes to high latitudes depends upon how warm it is in the tropics. And in particular in the western Pacific where it's warmest. And both the atmosphere and ocean transports depend upon the temperature there. You can see that the temperature there, this is again determined from the ocean cores, but it's gone up and down by 3 or 4 degrees Celsius from ice age to interglacial period. And there were some interglacial periods that were warmer than the present one, like this one 400,000 years ago. But the warming that's occurred in just the last century has taken us up to a level which is within less than a degree of the warmest interglacial periods. So that's one of the reasons for saying we'd better keep additional warming less than 1 degree Celsius. And but if we look at these criteria, the melting of the ice sheets, we know that in the summer you get melting on the surface of Greenland. And this was the red area is the region with summer melt during 1992. And as a function of time, the area with summer melt has been increasing as the planet gets warmer. This is the amount in 2002. And in 2005, the area with summer melt was even larger. And what happens with that meltwater is it doesn't run all the way to the edge of the ice sheet and then go into the ocean. It'll find a low spot on the ice sheet and burrow a hole to the base of the ice sheet, a so-called mulin. This is a summer melt on Greenland, and there are some people for scale. But that water, when it goes to the base of the ice sheet, it lubricates the base of the ice sheet, and so it will tend to move downslope toward the ocean, the ice will, more rapidly. We have these ice streams on Greenland, which is a normal phenomenon. It discharges icebergs, these giant icebergs, to the ocean. But as this meltwater increases, then the speed at which this ice stream moves has doubled. This is the largest ice stream on Greenland, and it has doubled in the last 5 years. And the same has happened on other ice streams in Greenland. And initially it was argued by those people who are skeptical about how important this is, that, well, it also snows more because the Earth is getting warmer, so you get more water vapor in the atmosphere and more snowfall at the center of Greenland. And that's true, and we can measure that. But we can also measure the total mass of the Greenland ice sheet. Beginning in year 2002, there's a satellite called GRACE, gravity satellite, which measures the gravity field of the Earth with very high precision and allows you to see the changes in the mass of the Greenland ice sheet. And of course it increases during the winter as you get more snowfall, and then it decreases in the spring and summer as you get melting, and then increases again. But you can see that there's a long-term downward trend. The Greenland ice sheet losing mass now at a rate of about 150 cubic kilometers per year. And West Antarctica is losing mass at a similar rate. That two of them together add up to only about 1 millimeter of sea level per year, but it's the rate at which this is happening is increasing. And one way we can measure that, we don't have measurements of the mass with that precision we have that only for the last 4 years or so, but we do have measurements of ice quakes or earthquakes on Greenland. There are seismometers located all around the world that are used to detect where and how strong earthquakes are. And it's been found that the number of earthquakes on Greenland has been increasing as a function of time. Those earthquakes are actually ice quakes because they're detected to occur right at where these ice streams are discharging icebergs to the ocean. What happens is a portion of the ice sheet will surge forward suddenly, and then it'll grind to a halt on the solid surface that the ice sheet is sitting on. But it registers as an earthquake with a magnitude between 4.6 and 5.1 on the Richter scale. And the number of these doubled from 7 in 1993 to 14 in 1999, and now it's doubled again in the last couple of years. So it's an indication. The problem is the disintegration of ice sheets is a very nonlinear process, and so it raises concerns about possible large changes in sea level. Because we know if we look at the history of the Earth, when ice sheets disintegrate, they can disintegrate quite rapidly. During the last transition from the last glacial to the current interglacial, sea level went up at 1 point 20 meters in 400 years, which is 1 meter every 20 years. So ice sheets can, as they disintegrate, they can disintegrate quite rapidly. If we were to go to warming of 3 degrees Celsius and eventually get a sea level rise of 25 meters, that would cover many East Coast U.S. cities and essentially the entire state of Florida. And the entire nation of Bangladesh would be underwater. And about 250 million people in China live within 25 meters of sea level elevation. So obviously that's not something that it's not something you can adapt to. Compared to New Orleans, which had a few 100,000 people, this is a couple of orders of magnitude larger, or 3 orders of magnitude larger. So the question is, how long does it take the ice sheets to respond? And I think, based on paleoclimate evidence, the paleoclimate modelers had developed models for ice sheets which tended to respond on millennial timescales. But I think that those timescales for paleoclimate changes are determined by the timescale of the forcing, which is very weak and very slow forcing that changes over several millennia. I think that large ice sheet response are likely on the century timescale. And in fact, already the sea level rise has now increased to a rate of 3.5 centimeters per decade, which is 35 centimeters per century. That's still, it's more than a nuisance, but it's not as disastrous as it could be if we continue down the business as usual path. So I think I'll move along to the other nonlinear process is extermination of species. Because as the planet gets warmer, species will attempt to migrate. Because as you know, plants and animals can live within certain climatic zones. And you don't plant within in your garden something that can't survive in that climatic zone. But climates have changed in the past, and the plants and animals will move as the climate changes. But there's some. This present climate change is very unusual in the speed at which it is occurring, and species are already under stress for other reasons as humans are taking over much of the planet. And because of that, the pathways for migration are often blocked, and the rate now at which a given temperature line is moving is about, northern hemisphere land areas, is about 50 to 60 kilometers per decade. And now there's been a study of species in the northern hemisphere, about 1,700 species, and it's found that they are moving poleward at a rate of about 6 kilometers per decade. But the temperature lines are moving at about 10 times that rate. And as long as the total movement of the climate of the isotherms is small compared to the size of the region in which the species can live, then it's not disastrous, but it begins to be a problem as you continue to have movement in the same direction. Well, here's an example of a species that's threatened. There are, in the southwest United States, in the desert regions of Arizona, New Mexico, there are these so-called islands in the sky. You have mountains which have green areas. But as the temperature rises, the isotherms are moving up the mountain. So in effect, you're pushing things to higher altitude. And the mountains and the slopes leading up to the mountains are particularly biologically diverse regions. So in effect, you're pushing. So what's happened now in the southwest United States? One of the effects, one of the regional effects of global warming is as the planet gets warmer, the precipitation, you get more evaporation where there's water to evaporate, especially over the oceans. And so in the tropics, the tropical rain belt gets larger rainfall. But in the subtropics, it also becomes more intense in the sense that the atmospheric stability increases. So the dryness in the subtropics increases, and that includes, by the way, the Middle East and the southwest United States, the western part of the United States. So that what's happened now, that in the lower reaches of the forests on the mountain, it's become dry, and now there have been forest fires which have been particularly hot and devastating fires, which the forest then does not recover. The lower parts of the forest just become part of the desert. What was forest becomes part of the desert below. So this particular squirrel, which was identified as an endangered species about a decade ago, and its numbers had increased back to about 500 squirrels on the one mountain that it survives on. But now, after some of these fires a few years ago, it's now down to about 100 squirrels left. But anyway, it's just an example of how you push off the planet those species that live in alpine regions. And likewise, at the polar regions, there's no place colder for animals to migrate to. So it's a changing climate is a threat to polar species. And this is just an example of the regions that get drier as well as hotter are those which are in the yellows and oranges and reds. And as you can see, that does include the Mediterranean region. So these, and actually if you look at the history of climate in the United States, when you go back to times when it was warmer, there was an extreme drought in the western United States. So I think there's a danger of regional climate changes that are also important. So we would like to look at the future for different scenarios. This is the annual increase in carbon dioxide in the atmosphere. And when Keeling began his measurements back in 1958, carbon dioxide was increasing at less than 1 part per million per year. But as the fossil fuel use has increased, the growth rate of CO2 in the atmosphere has increased proportionally to that, and it's now about 2 parts per million per year. If we follow business as usual, it will be 3 to 4 parts per million per year by the middle of the century. And I contrast that with what I call alternative scenario. This is what we would need to do if we want to keep warming less than 1 degree Celsius, additional warming over and above that in year 2000. And that scenario, by the way, was designed in an analogy to how the world handled the earlier global atmospheric crisis, which was the ozone layer, when Rowland and Molina reported in 1973 that chlorofluorocarbons might destroy ozone. It was just a theory, but it had an impact on, they stopped making any more factories at that time because people stopped using hairspray and deodorants that were powered by chlorofluorocarbons, aerosol spray cans, and so they didn't need any more factories. They just continued to produce at about the same rate. But chlorofluorocarbons are also used for refrigeration, which is important, and so that usage started to increase again. But then the ozone hole was discovered over Antarctica, so then it was no longer a theory, it was a real problem. And the Montreal Protocol came into effect, and the protocol said that developed countries had to phase out chlorofluorocarbons within quite rapidly, within a few years. And developing countries were allowed to continue to increase their production of chlorofluorocarbons for up to 10 years, but they had to be aware of the fact that 10 years later they're going to have to phase them out also. And the developed countries provided technology assistance for replacements to chlorofluorocarbons, and so that all worked very well. Developed countries provided about $100 million a year to India and China to close down their factories for chlorofluorocarbons, and now the production of those chemicals has gone down, and the ozone layer seems to have stabilized, and it will heal itself over the next 50 years. Now, but what's happening with carbon dioxide is the amount of fossil fuel use and emissions of CO2 increased at about almost 5% a year up until 1973, when the Arab oil embargo woke everybody up, and they decided that we better try to be more efficient in the use of fossil fuels. And there were some standards put on vehicle emissions. Since then, the fossil fuel use has continued to increase at almost 2% a year. But that's a slower rate than it was increasing then. Well, if we're going to have the alternative scenario, this is now what we call business as usual, this rate of increase. If we're going to have the alternative scenario, it's got to start to decrease. So that's going to, and you know, technically that's possible. If this, for example, is if you just replaced vehicles with ones that had a 30% greater efficiency, which the National Research Council in the U.S. agreed that we have the technology right now to have vehicles that are 30% more efficient. In that case, instead of a business as usual growth in emissions from vehicles, you could go on a path that had actually decreasing emissions as the vehicles slowly got replaced by the newer ones. Eventually, you're going to have something more because the number of cars keeps increasing as a function of time. So if you want this to continue to come down, you're going to have different technologies, but we're going to have to do that anyway because oil is going to run out at some point anyhow. So, and similarly with buildings, there's a potential with technology now to improve efficiencies by 50%, reduce emissions by 50%. But now part of the problem is that carbon dioxide that we put in the atmosphere from fossil fuel burning, the ocean and biosphere, mainly the ocean, take up this carbon dioxide, take up part of it quite rapidly. Within 25 years or so, about half of it is taken up. But then the uptake slows down because the CO2 that's added to the ocean exerts a back pressure on the atmosphere. And you're not going to be able, and it's not going to take up all of this CO2 until it forms carbonates and sediments, sediments to the bottom of the ocean. So even after 500 years, about a quarter of the carbon dioxide that we put in the atmosphere is still there. So we cannot burn. So a most important fact, which is not yet understood by policymakers or the public, is that we cannot burn all the fossil fuels without creating a totally different planet. The amount that we've burned so far is this dark purple. And that's increased CO2 from 280 parts per million to 383 parts per million. Well, if we go beyond 450 parts per million, then we're going to have global warming of more than 1 degree Celsius. So we're going to have to, so I argued in a paper about the year 2000 that we'd better try to keep CO2 below about 450 parts per million. Now we're beginning to realize that maybe even that's too high. So we're really already at and the point is that oil, we're going to burn this oil because it's just too convenient a fuel, and it's burned in vehicles. It's impractical to capture the CO2 coming out the back of a vehicle. And you're not going to be able to tell the oil producers, you're not allowed to drill your oil. So we're going to use this, and that's about enough to take us up close to 450 parts per million, the oil and gas. So that means that the practical way to keep CO2 at about 450 would be to say, okay, we're only going to use coal where we burn it in power plants, where it's practical to capture the CO2 and sequester it. And we're not allowed to use tar shale unless we do it under a similar condition that we're going to capture the CO2. So I would say the way we could keep CO2 at about 450 is using coal only in power plants. That means we're going to have to phase out the old power plants. We're going to have, within the next few decades, we're going to have to bulldoze the old power plants, replace them with something else, either capture the CO2 or some other form of energy. And the problem is, if we just continue to use oil and gas the way we're doing, increase more and more every year, then there's going to be such a demand for oil and gas that we're going to start squeezing oil and gas out of coal or out of unconventional fossil fuels. And therefore, it's important to start using these oil and gas more efficiently. And there's tremendous potential for doing that, but it's not going to happen if you don't have some incentives, and that means a tax. And no politician likes to use that word. But we have no choice. And we're also going to have standards on vehicle emissions, because even a tax is not, There are so many people, plenty of money. If you don't have standards for vehicle emissions and building emissions, you're still going to have a problem. But there are other climate forcings. If you remember an earlier chart, carbon dioxide is only about half of the present human-made forcing. Methane, nitrous oxide, black carbon, you add them all up, they're significant. And some of these we could decrease, and that would allow us to have a little more CO2. And we're probably going to need that because it's so difficult to solve the CO2 problem. But we're likely to pass the dangerous level of CO2. So I think we're probably going to have to draw down the amount of atmospheric carbon dioxide. And that's possible partly by means of improved agricultural practices, no-till agriculture, and improved forestry practices, minimizing the deforestation, and even by burning biofuels in power plants. Because if we burned biofuels in power plants and captured the CO2 and sequestered it, you could sequester it beneath ocean sediments where it's inherently stable. You don't have to worry about it leaking out again. So we're putting it back where it came from. And as the biofuels, as you grow plants to produce these biofuels, those plants are drawing CO2 out of the atmosphere. So you could reduce the amount of atmospheric CO2. But not if you're using all the biofuels to make ethanol for vehicles, which is just not a very practical way to power the vehicles. We're going to have to find a way to power vehicles that does not use fossil fuels. But so it's a big challenge. And I like to imagine that the Midwest will come to the rescue of the coastal states by producing biofuels that draw down the atmospheric CO2. But one other thing that I like to make clear, because there are politicians who are saying, oh, it doesn't matter what happens in the United States because China is going to pass us, and they will. Within 1 or 2 years, they're going to pass the United States. They're building power plants at such a tremendous rate, 1 power plant every week, or even slightly faster than that, burning coal, that they're going to pass the United States as the current emissions. But that's not what causes climate change. It's the CO2 in the atmosphere. And that depends not on current emissions, but on integrated emissions, or cumulative emissions over time, because a large fraction of the CO2 stays there practically forever, more than 500 years. If you look at the climate impact, or just look at the cumulative emissions, the United States has produced more than 3 times more than any other country. And that's going to be true for several decades into the future, even though China is going to be gaining on us. But the United States is still going to be the largest producer. And furthermore, we have an additional responsibility because the United States is the country that blocked effective implementation of the Kyoto Protocol. It's not very effective because the United States has not been involved. And the effect of Kyoto Protocol, one of the most important effects would be the transfer of technology to China and India so that they don't need to have so many power plants. They're very inefficient. China and India, the technology there is much less efficient and produces more CO2 than is necessary. But anyway, so the summary is that it's still possible to achieve what I call the alternative scenario and keep the warming at about 1 degree, but it's just barely possible. And if we go even 10 more years at business as usual, that would be, business as usual is increasing emissions at about 2% per year. And emissions by year 2015 would be 35% higher than they were in year 2000. So that achieving reducing emissions to 70% of 2000 by the middle of the century is just not practical, because you would have in place the infrastructure that's producing that CO2, power plants primarily. So we really have to get going, and that message has still not appreciated by policymakers. I guess that's the last chart, so we can discuss this.
Thank you, Joe. Any questions? Kiva?
Yeah, actually, we have two. One is Paul Cruiser, who was here a while ago, mentioned that we move into biodiversity. So we're going to increase considerably the N2O emission. How is that balanced? And the second question is, if anybody tries to measure or remember whether what the composition we see in this air bubble in deep I-70 really correspond to the actual composition of the atmosphere when they go.
Okay, yeah. As I mentioned, carbon dioxide is about half of the anthropogenic forcing. The second largest forcing is methane, and the third and fourth are chlorofluorocarbons and N2O. And this alternative scenario actually assumes that we will reduce methane emissions and get the absolute amount of methane in the atmosphere to actually decline. But it assumes that nitrous oxide will continue to increase, but not at the most extreme rates, but slow down somewhat. The N2O comes particularly from fertilizing fields, and we're wasting. If that fertilizer were applied with the amount that's needed in order to get the increased growth, then the emissions of N2O to the atmosphere would be greatly reduced. It's just that enough is put on, an excess amount is put on, and then a lot of it ends up, instead of going into the plant as nutrients to the plant, it's ending up in the atmosphere as N2O. So we could reduce that, but Crutzen is probably right that if we have more and more agriculture to grow more biofuels, that we will, there's a danger that we will put more N2O in the atmosphere. And so that's another reason that trying to grow biofuels to power vehicles is just not a very effective way. You can argue about whether it's reducing the net. It's probably producing less greenhouse gases than burning fossil fuels, but not that much less. It's probably, the estimates that were made in the United States were, well, it's producing 70% as much or something, but it depends. And it depends very much on what fuel you're using. If you grow corn and then try to make biofuels out of that, it's just not, you barely gain anything. And if N2O is really increased, maybe you don't gain anything at all. But if you grow switchgrass or some cellulosic fibers, natural grasses, and you grow those with a no-till agriculture, and you don't put lots of nitrogen on, then that may be relatively more effective. It will still produce some greenhouse gases, but if you're then using the biofuels in a power plant and capturing the CO2 entirely, then you definitely are gaining, and you're definitely going to reduce greenhouse gases. But if you use it in vehicles so that the CO2 just goes right back in the atmosphere, then you're going to lose. And so I think we're going to have some other sort of vehicles. And, if you've seen this little movie, Who Killed the Electric Car, I think the answer was Detroit killed the electric car because it was too threatening to the fossil fuel powered vehicles. But we may, that we're going to have to find something. It could be electric cars, and then you produce the energy. Question of how you make the energy at the power plants. But anyway, so the second part of your question was, have we verified that those bubbles of air really have the gas amounts that existed at the time the bubble was sealed? And yeah, there's been a lot of effort to do that. And one gas in which it doesn't work very well is the N2O. And that's why I only showed methane and CO2. N2O, when there's some dust in the ice with some organic stuff in it, then it turns out that it messes up. You get some N2O from some reactions that have occurred over the years, and so it doesn't check out. And I'm not really an expert in exactly how those checks have been done. Of course, we have ways of doing it for the very recent time, where we have measurements, but how you verify it on the long run is mainly consistency. You get the same answer different from Greenland and Antarctica, and then there are different ways of doing it with ocean cores. So that's not quite right. But in any case, there's a very high degree of confidence in the carbon dioxide and methane amounts in the ice cores.
About a year ago, in May 2006, there was a meeting in Santa Fe on global warming, in which many skeptics gathered over there. And there were two lectures, particularly, that I want to ask your response to. One was given by the convener of this Santa Fe meeting. He was talking about the temperature in Greenland. And he presented his result, there was no change. Another series of talks, or another session, was about cosmic rays affecting the clouds and the temperature, and there's one person in Israel, in the university. I wanted to hear your response to these two criticisms.
Yeah. Greenland is the worst place on the planet to measure the temperature if you want to find a place where the temperature change will resemble the global temperature change. It's very sensitive to the ocean dynamics around Greenland, which depends upon the rate of deep water formation, and it's very sensitive to the weather patterns around Greenland. But in fact, Greenland for several decades was cooling off. If you look at Greenland over this entire period, going back to late 1800s, and all you have is measurements at a few spots around Greenland. But it does look like its temperature change over that period is comparable to that of the rest of the world, and it has been warming significantly over the last 10 or 15 years. That's why we're beginning to see changes occurring there. So you shouldn't use measurements at one spot to tell you what global temperature is doing, but even if you do, Greenland is now starting to agree more with the rest of the world. The thing about cosmic rays, yeah, there have been all sorts of ideas about things that can change climate, and both natural and human-made, and cosmic rays are one of the things. It's suggested that cosmic rays will affect the nuclei in the upper troposphere and affect the cloud cover, and they try to find correlations. There are many things that might have some influence, but now humans, this forcing by these changes in greenhouse gases is so large that all of the things which skeptics had used to try to point to as alternative ideas for climate change are just kind of getting overwhelmed. so that solar, a more viable mechanism, natural mechanism, is changes in the sun. And there are correlations of climate with the changes on the sun. But we now are measuring the sun very precisely, and we know its brightness changes by about 0.1%. And if you then try to infer the changes on longer timescales when we didn't have satellites, but use the visible features on the sun that correlate with the brightness, then you would infer that, well, yeah, during the Little Ice Age, the sun was maybe 1/10 or 0.2% dimmer, and that may have been a cause for the Little Ice Age. But we now quantitatively can compare those forcings, and the greenhouse gas forcing is now several times larger than any solar variation. So all of these points made by the skeptics have, kind of fell by the wayside. It's not that some of these other things may be important for minor features, but humans are now in control, and greenhouse gases are the dominant thing.
Look at far enough. It's a climate warming university.
Pardon?
If you look out far enough, it's a climate warming university.
If you look at what?
Look out far enough.
If it weren't for human-made greenhouse gases, then we would have been headed toward the next ice age. The dominant mechanism on this longer time scale is the fact that the time at which the Earth is closest to the sun is now in January. And it changes with 23,000-year cycle. It goes through the entire calendar, 23,000 years. So that's why half a cycle earlier, the Earth was closest to the sun in the summer. And so the ice sheets were melting, and sea level went up rapidly. Now, closest to the sun in January means that in the northern hemisphere, the summers are relatively cool, and the winters are relatively warm. And therefore, you get more snowfall in the winter than you would 10,000 years ago. And you get, and so you should be able to start to form an ice sheet in northern Canada. And it's cool enough in the summer that it could survive over the summer. So we would have been headed toward an ice age. But the mechanism by which that happened, but now the CO2 increases are just totally overwhelmed that very weak forcing. That forcing, the natural forcing due to the seasonal change in the seasonal distribution of sunlight is about 1/4 of a watt averaged over the planet. But the human-made greenhouse gases are now a couple of watts. So it's an order of magnitude larger. Humans are now completely in control of that. So we're not going to go to another ice age. And we won't have one unless humans become extinct, because you only need a thimbleful of chlorofluorocarbons in order to prevent an ice age. And so why would humans let an ice age occur? It's trivial to avoid it. The problem is the opposite. We have to avoid going off to a greenhouse heated Earth. Yeah, so the problem is that, well, first of all, the technology is not quite ready. There are a couple of power plants on small scale that are capturing CO2. In one case, it's being then injected into oil wells to enhance the recovery of oil from the oil wells. But the technology to do this on the scale of large power plants is still a few years off. There's a project in the U.S. to do that, and one in Europe also. But anyway, the problem is that it will increase the cost of power from the coal power plant by 20 or 30 or percent. But still, coal is so darn cheap that it will probably be competitive with any other form of power. But somebody's going to have, but the ratepayer, somebody's going to have to pay for that, and so it'll be a negotiation. If you want, it should be. This becomes a matter of opinion, and my opinion means no more than anybody else's with regard to what you do politically, what citizens want to do. But I think if you just have a gradually increasing price on carbon emissions, it's going to drive technology, and it will drive both the increase in renewable energies that don't produce carbon dioxide, but also it'll drive energy efficiency. And then the different sources of power can compete, and probably one of them will be. Fossil fuels are amazing. That's the problem. You've got so much energy locked in just a small volume that a person can sit behind a wheel of a vehicle that has the power of 500 horses, and an engineer can sit behind an engine, a train that has a power of 100,000 horses. It's hard to get that energy that compressed. I mean, it was formed over hundreds of millions of years, and it's a very valuable commodity which we should really preserve, conserve. That's why we should have. You can mine in some places. You can mine it for almost nothing, and it takes like 50 cents to get a barrel of oil in Saudi Arabia. It's so easily available. But I started to wonder, what was the question? Coal-fired power plants. Yeah, so who's going to do that? Well, the developed countries, I think, should first be doing that via their need. There is a need for power in developed countries, and as we develop that technology, we're going to have to make that available, as we did with chlorofluorocarbon technology.
One more question, Dan. What is your opinion on two things? One, at the end of the day, the cost for action is depending on models prediction. And the model is calibrated based on past decades of couple of tens of degrees, and we know that we're trying to predict things that really happen in the past. And we know that there are not only positive feedback, but also negative feedback on the system that we're not sure if we all include them or not. How confident can we be based on these models with this call for major global action? Is one point. The other one, you mentioned this preventing ice age. This is part of another step here. Sort of position that we all the time have to face a change. So either cooling or warming, and they're always bad and good benefits to each one. So maybe we just have to face climate change and look for the good signs and the good problems.
Yeah, yeah. The thing is that the climate sensitivity is not based so much on climate models as it is on the paleoclimate data. And any feedbacks that can occur did occur in going from ice ages to interglacial periods. So it is true that if you just use models, which is what they're doing 25 years ago, Jarny did his study, you had to be very uncertain as to do you have all the processes in there. But all the processes are there in the real world. So that sensitivity of 3 degrees for double CO2 is very solid. So that what we've learned, and I really didn't have time to get into this in this talk, but I have a paper in press in the Philosophical Transactions of the Royal Society, in which we look more carefully at the paleoclimate changes. And what we realize, yeah, you're right, that you don't a priori know how much positive feedback you have versus negative feedbacks. That it turns out that both the water cycle and the carbon cycle have strong positive feedback, and they dominate. And it's very understandable in the case of the water cycle. The major feedbacks are, as the planet gets warmer, the atmosphere holds more water vapor. It's a very strong greenhouse gas. As the planet gets warmer, snow and ice melt. Again, it's a very strong positive feedback, and the planet absorbs more energy. But what we've realized in just the last couple of years is that when Charney defined this problem, we implicitly were taking some other processes as being slow. So when we defined climate sensitivity, we're including snow and ice changes, snow changes, and sea ice changes, and water vapor changes. But you're taking the other things as fixed boundary conditions, including atmospheric composition is a boundary condition or a forcing, and the ice sheet area. You just assume that Antarctica is there and Greenland is there. But what we're finding is that things that we did not include are actually beginning to change on decadal timescales. In particular, there are forests that are beginning to move poleward. It's a strong positive feedback because plants are designed to absorb visible radiation for photosynthesis. So they're dark. Evergreen forest has an albedo of about 5%. And so as you replace tundra with forest, it's a very strong positive feedback. And as the tundra melts, methane comes out. So the greenhouse gas is a positive feedback. Well, we knew that from the paleoclimate. When the planet gets warmer, greenhouse gases come out. And ice sheets are beginning to respond already on decadal timescales, at least not in their area so much, but in their albedo, because you get this summer melt. They get darker, and they get darker sooner. Springtime melt begins earlier. The melt season becomes longer. So it didn't have to be, but it turns out positive feedbacks dominate. And that explains why climate was so sensitive over these longer time scales, because positive feedbacks predominate. And in this paper in press, we talk the climate literally whipsaws between ice ages and interglacials due to very small forcings. And if you go back far enough, the planet whipsawed all the way to frozen to the equator. The ocean froze over. The last time was 540 million years ago. But CO2 became small enough that it froze all the way to the equator. And we'd always wondered, why the Earth, that never happened with the Earth. Because we know the sun was dimmer when the Earth was younger. Well, it turns out it happened a number of times. The most recent one was 540 million years ago. And we thought, well, it couldn't have happened because how did the Earth unfreeze? Because once it's frozen, it's so bright, it's not absorbing much sunlight. But what happens is volcanoes continue to go off, even though you've got a frozen Earth. And there's no weathering. It's so cold, so the CO2 just stays in the atmosphere. And eventually you've got so much CO2 that you can overcome this greenhouse effect. And suddenly, once you start to get melting at the equator, then the positive feedback works the other way, and it melts all the way to the poles. You had a totally very hot planet. So the Earth's climate is very sensitive. The paleoclimate record shows us without any doubt, positive feedbacks predominate. Clouds are included in you can't model them well. It turns out in the models they're almost neutral. They don't cause much of a feedback. But they're included in the paleoclimate. When the climate changed, This climate sensitivity that we infer includes any cloud effects that occur.